Hello, everybody. This is Sunday. It's January 29th, and we are heading into week 4 of our online astronomy course. Module 4 is all about light, and this is the last of the first 4 modules that describe the history and science of astronomy. And in the next modules, we'll start applying what we've learned to understand the planets, our sun, other stars, and other galaxies. So, before we dive into here, I want to tell you that because we are finishing up the first 4 modules, your first exam is going to start the week after next week. So not next week, but the week after next. So the first exam on the first 4 modules will open up on Monday, February 6th, and it will close on Sunday, February 12th. The exams are open book. You can use your homework if you want. No other resources are allowed. And you can take every exam twice. You can take the exam twice. If you don't like your score the first time, then take it again. And if you take it again, I give you the average of your 2 scores. So there'll be more about that. I'll talk more about that next week. But let's get started on understanding light. Now, astronomers have to be experts at understanding light because that is pretty much all the information that we get from stars. All we can do is look at the stars. The stars are much too far away to send a spacecraft to them to study them. And so all we can do is look at the light from stars. Now, there are a couple exceptions. We do receive neutrinos, which are subatomic particles that we'll talk about later. And we also can study gravitational waves from merging neutron stars and black holes. And those we'll also talk about later. But the vast majority of the information we have about stars comes from light. So, what is light? Well, light is what you see, but what is it? What makes up light? And it's not an easy question. And in fact, Isaac Newton thought about it and got it wrong. And other people thought about it, thought they had the answer, they got it wrong. And today we do understand what light is. And light is a wave. Now, what is waving for a light wave? Water waves for a water wave, air vibrates for a sound wave. What is it that is waving for a light wave? And the answer is electric fields and magnetic fields. Now, you're all familiar with magnetic fields. If you use a magnet to pick up a paper clip or something like that, you're using the magnetic field to lift up the paper clip. You're also familiar with electric fields because if you've ever taken, clothes out of your clothes dryer and you feel that static cling, and maybe if you run an article of clothing over your hand, so you run it over your hand, you can feel the hairs stand up on your hand, and those hairs are responding to the electric field that is around those clothes. And the electric field is due to electric charges on the clothes. So, electric fields and magnetic fields, part of everyday life, and they make up light waves. And the electric fields and magnetic fields both vibrate back and forth. Their direction changes back and forth. And so an electric field might be going this way, then it's going in the opposite direction, then it's going this way, then it's going in the opposite direction, back and forth. And the magnetic field's going up and down and up and down. Both of them changing direction together. And they carry energy. And so we can think of an electromagnetic wave as these pulses of electric and magnetic energy, or to put it in one word, electromagnetic energy. And so light is an electromagnetic wave. And sometimes, in the wave, when there's a pulse in the wave, that means that there's a lot of energy there. And when those pulses die away, there's not much energy there, and so on. And how often do those pulses happen? Well, those pulses happen about 100 million times per second. So extremely rapidly. So that is what an electromagnetic wave is. Now, we can picture this as a water wave, as a wave that goes up and down and up and down. And that's how light is usually pictured. But there's nothing going up and down for light. Those are just showing the directions and the direction changes of the electric and magnetic fields of the light. Now, there are these pulses, so light is a string of these pulses. And if a light wave is coming towards you, there's one pulse after another, just along a line that's going to your eye. That's how we see things. Light is reflected from something. Like right now, the light is coming from the screen you're watching me on, and that light is coming to your eye. So that's how we see things. Those pulses are carried toward us. Now, there's a distance between those waves, those wave-like pulses. And the distance, the length of one wave is called the wavelength. And the wavelength of light is very, very short. And in fact, so short that we have to use a new unit to talk about them. Remember, we've talked about meters, which is about a yard long. There's a centimeters. And a centimeter is about a little bit under half an inch. There's 2.54 centimeters in an inch. And so we are going to be talking about smaller than centimeters. We're going to be talking about billionths of meters. And a billionth of a meter is called a nanometer. A nanometer. And the color of light tells you, the wavelength of the light tells you the color of the wave. And so here's a rainbow behind me. You can see the white light of the sun. The sun consists of all colors of light. And the water droplets in the air break that white light into its component colors. And if you take a look, you can see that there's violet light at one end. And that violet light has the shortest wavelength. It's about 400 nanometers, 400 billionths of a meter. And then going on through the other colors up to red, and red light is about 700 nanometers. So 700 nanometers in length for a red wavelength, about 400 for a violet or blue, as it's sometimes discussed, wavelength. So that's what light is. It's an electromagnetic wave. And that's what people thought it was. Okay, light is a wave. Light is a wave. And then they discovered, no, that light really is a stream of particles, a stream of massless particles, just pure bundles of energy. And the energy of a light wave is carried by these little tiny bundles of energy. So each of these pulses contains many, many bundles of energy. And these bundles of energy are called photons. And so every second, if you're looking at your screen, there are many billions of photons per second entering your eye. And so the world doesn't look grainy. The world looks smooth and continuous because there's just so many photons entering your eye. And so it's photons that carry the energy of light. And the photons, It turns out that the photons that have the most energy are at the violet end of the visible spectrum, and the photons with the least energy are in the red end of the visible spectrum. Now, when I say the most energy and the least energy, I'm talking about just for the visible part of the electromagnetic spectrum. But the electromagnetic spectrum, all of the wavelengths of light, stretch over a huge range, and visible light's only a small part of that. At the short wavelength end, and that means at the very energetic end, very energetic photons, we have gamma rays. And after gamma rays, less energetic slightly, are X-rays. And then we get into ultraviolet rays. And you know, the ultraviolet rays are dangerous because they can cause you to get a sunburn. And so we use sunscreen against that. And then we reach the visible wavelengths. We can go from violet to red at the other end. But past red, there is infrared light we cannot see. And then beyond that, there is things like microwaves and then radio waves. So yes, radio waves, if you're listening to the radio, that information is being carried by light. And when it reaches your radio, that information is changed into sound and you can hear it. So, these divisions of light are largely because of historical reasons or because of the way they interact with matter. But all of light, from gamma rays to radio waves, all that light is the same. It's all pulses of electric and magnetic energy, and it all travels at the speed of light, which is the fastest speed that anything can travel. So that is what light is. Now, I've already talked about the spectrum of sunlight and how sunlight consists of all the visible colors. And the sun is an example, the sunlight is an example of something called black body radiation. And black body radiation is really very, very important for astronomy. And the idea is that any object with a temperature above absolute zero, and that includes everything, that includes you, that includes the stars, everything that has a temperature above absolute zero gives off black body radiation. This is just light that has a particular spectrum. Not all of the colors, not all of the wavelengths get the same energy. There's an energy peak. And where that energy peak is depends upon the temperature of the black body. For instance, our sun is very, very hot on the surface. It's about 5,772 degrees Kelvin, degrees above absolute zero. And it's so hot that it glows in visible light. So its peak is in the visible part of the electromagnetic spectrum, the total spectrum of light. On the other hand, we as human beings have our own body temperature. It's about 98.6 degrees Fahrenheit. It's around 300 or something degrees Kelvin. But we are giving off black body radiation too. And you can feel that. In fact, let's feel it together. So let's take your hand out in front of you, not touching you, and slowly move your hand toward your forehead, not touching your forehead. And you feel some heat there. That heat is black body radiation that your body is giving off. That's what we call heat radiation. It's in the infrared part of the spectrum. Our eyes cannot see the infrared wavelengths, and so The heat radiation is invisible to us, but you know that there are special cameras that can see the glow of a person's heat in the dark. And so they are sensitive to the infrared. And so you're glowing right now with about the same intensity as a 100-watt light bulb. You're giving off that much light. And it's invisible to us. We can't see it. So there is a relationship between what that peak wavelength is and the temperature, and it's called Wien's law. And you'll find about that as you read your textbook and as you do the homework in your module. And this is really cool because it turns out that cooler objects, you know, if you have a burner, if you happen to have an electric stove, or if you've ever heated up metal in a fire, you know, it first begins to glow a dull red. And so red corresponds to cooler objects. And as you heat it up, it gets hotter and hotter and hotter. And most of the light then shifts toward blue colors. And our eyes perceive that as glowing white hot. And so blue objects that glow blue because of their color, this is because of their color, those objects are hotter. And red objects that glow because of their color that are less hot. And so the color of the stars tells us the temperature of the stars. If you look up in the sky and look at the constellation of Orion, if we ever get to have a clear night to see the stars, take a look at the constellation of Orion and the star, the prominent star that is in the upper left-hand corner, that is the star Betelgeuse. It's a red giant star, and it looks reddish because its surface is relatively cool in the 3,000 to 4,000 degree Kelvin range. On the other hand, if you look at the bottom right-hand star, that is Rigel, and Rigel is blue-white. It's a very, very hot star. And so the colors of the stars in the sky are due to their surface temperatures. And so that's one way that we can tell the surface temperature of the star, cooler stars from hotter stars. Blue is hot, red is cool. And I know that seems backward because we associate, you know, blue with ice and things like that. No. For objects that are giving off black body radiation, blue is associated with the hotter colors and red with the cooler colors. So let's take a look at the sun spectrum. Now, the spectrum is just all the colors of the light spread out according to wavelength. And in fact, that's what a rainbow is. A rainbow is showing you the spectrum of the sun from blue here all the way up to the red. Okay. So what I want to do is take a look at the sun spectrum. And what you can do is you can pass sunlight. You can pass any light source, in fact, through a triangular piece of glass called a prism, and that will break the light into its component colors. And when you do that with sunlight, here's what you get. This is the sun's light. The short wavelengths, the most energy, is down here at the bottom, the blue wavelengths, going up through all the colors of the rainbow up to the red, the longer wavelengths, the least energetic photons in the visible range, are up here at the top. So about 400 nanometers down at the bottom for the blue, about 700 nanometers up at the top for the red. And all the colors of the rainbow are there. In fact, we call this, because there's a continuous range of colors, we call this a continuous spectrum. And so the sun gives off a continuous black body spectrum. But if you look, you can hardly miss it here. Look at all of these dark lines in the spectrum. And here, just to make it clear what's going on, is that this is really one very long spectrum. And so it goes along here, and then it meets up on the left-hand side, goes to the right, left-hand side goes to the right, and so on. And we see these lines. You see these dark absorption spectral lines. And these spectral lines are where light has been absorbed by the gases and the cooler gases in the sun's outermost layers of its atmosphere. And they absorb some of the light, and so some of the continuous spectrum is missing, and it appears dark. And we'll find out that this is because the atoms in the sun's atmosphere absorb a photon of light from the continuous spectrum. And when they absorb a photon of light from the continuous spectrum, the electron that orbits the central nucleus of the atom, an electron jumps from a lower to a higher orbit. And so it's used that energy to jump up to a higher orbit. And that removes the light from the spectrum, and so a dark line appears. And the really cool thing, there'll be more details about that in your module and in your homework, your practice quizzes and your retake quizzes. But what is really cool about this is that every element has its own spectral line fingerprint, a different pattern of spectral lines. And so looking at all the spectral lines that are in this the spectrum, astronomers can tell all of the elements that make up the sun. Not only that, but they can figure out how much of each element there is. So reading these spectral line fingerprints is really very important, and we'll talk more about that in one of the chapters that come when we talk about stars. Also, it turns out that atoms can emit light. If atoms are hot, atoms of a gas are hot, and they're not really dense, they're spread out. So atoms of a dispersed gas, not very hot, hot but dispersed gas, the electrons in those atoms are in higher orbits. They're farther away from the nucleus. And when they drop down closer to the nucleus, they emit light. And so that is the source of a lot of the beautiful glowing gaseous nebulae that we see in space. I've made some videos about the continuous spectrum, emission lines, and absorption lines for you to watch for this module. So please take a look at those. Now, there's one more thing, one more piece of information we can get from light. And that is we can tell a star's speed toward us or away from us. And this was discovered for sound by a man named Christian Doppler. And Christian Doppler had noticed this, and I'm not sure how, but he studied it. And he studied it by putting some trumpet players on a railroad car and had the railroad car go by him. And those trumpet players would, play a note on their trumpet, just a single note. And Doppler would notice how the sound changed as the car went by. And maybe you've noticed the same thing too. Maybe you've been at a railroad crossing and here comes a train going by blowing its horn. And maybe what happens is that as it goes past you, it's approaching you. And so you hear it approaching, and as it's approaching and blowing its horn, you hear a higher pitch, a higher frequency. And so as it's approaching, you hear a higher frequency. And then as it's moving away, you hear a lower frequency. And it sounds like this. Meow. Let's do that again. Meow. Now, what's happening is that as the source is approaching your ear, it's catching up with its own sound waves that it gives off. And that compresses the sound wave and makes it shorter. And that means that more waves are hitting your ear every second. And so the frequency, you hear a higher frequency. And that's the part of it. Now, as it's moving away, you know, as it's moving away from your ear, then it's moving away from its own sound waves. And it's stretching those sound waves out. And so fewer sound waves are hitting your ear every second. And so you hear a lower frequency. Meow. And so the whole effect is meow. Same thing for sound waves. I mean, same thing for light waves. If a source of light is approaching you, it's catching up with its own light waves. It's compressing those light waves, and more of them. They're bunched together more, and more of them hit your eye in a second. That's the frequency. Higher frequency, shorter wavelength. You know that that's a bluer light. And so if a star is approaching us, its light looks a little bit more blue. Now, it's not noticeable because stars aren't moving that fast compared to the speed of light. You know, light can reach the moon in just a little bit over a second. And so stars are moving much, much more slowly than that. So the color of stars is because of their surface temperature, not because of the Doppler shift. But there is a slight shift in the positions of those dark lines. And that is something astronomers can measure. And so we can measure the speed of stars. So if the star is coming toward us, it's catching up with its own light waves. And we see those spectral lines shifted toward the blue end of the spectrum, just slightly. And we can tell the star's speed. At the same time, if the star is moving away from us, then it's moving away from its own sound waves. And that means its own light waves. And that means it's stretching those light waves out. And the wavelength increases. And that means that there are fewer light waves hitting us per second. And so the spectral lines are shifted to the red. So a star coming toward us has a blue shift. A blue shift to the blue side of the spectrum. And if this is moving away from us, the spectral lines are shifted to the red end of the spectrum. So all sorts of wonderful information we can get from light waves. So I really hope you enjoy learning all about light. And I do have a couple of things to show you in Stellarium. But before I go to Stellarium, I'll just tell you that if we do ever get some clear nights, try to go out and see the comet. This is comet C2022 E3F. I'm sorry, ZTF. Okay. And I have on my iPhone a little app here. You can get an app with that name on it. And if I just press that app, what it does is that it brings up the sky. There it comes. Okay. So there is the sky. I'm pointing the camera up to the sky. It's the back camera. So it looks like it's tilted down towards you. That's because I'm pointing the back of the phone up to the sky. And if I just move this around, you can see the constellations. It's a free app. And if I move it to the right place, and it's to the north, and if I tilt this to the north, you know, this to the north, then the screen isn't facing you, obviously. So that's not going to work very well. But if you tilt it to the north, there's a big red circle around the comet. That's all this app does. This app shows you where the location is night by night of the comet. So you can, I know you can get it at the, you know, the App Store for Apple products. I don't know about Android or other things, but take a look because it's pretty cool and it's free and you can use it with your smartphone. So let's go to Stellarium here. Well, here we are, familiar scene. You know, we're looking at Stellarium. We're facing south. And this is tomorrow night, Monday night. This is the 30th of January. And there is Orion in the south. And there is the red giant star Betelgeuse that I mentioned before. And here is Rigel. I don't know if you can see that or not, but there we go. There is Betelgeuse and there is Rigel. But look at the time. The time is 9:50 in the evening. It's a weird time. Why did I pick that? Let's go up here. This is only going to be happening tomorrow night. And here is the moon. The moon is just about at first quarter phase. So I'm just going to bring it here to the center and zoom in on it. There we go. And yeah, there is the moon, and I'm going to drag this toward the center and zoom in on a little bit more. There we go. And there is Mars right by it. And this is going to be a near occultation of Mars. A near occultation of Mars. And as I go from night to night here, or from minute by minute, let's just advance this minute by minute. This is going to be hard because the moon's going to move a little bit. But what's happening here, minute by minute, is that Mars is passing right by the moon, minute by minute. And this is a near occultation of Mars by the moon. In fact, if you live south of here, if you were in Houston, you would actually see the moon move in front of Mars. And if what's actually going on here, it looks like, well, it's hard to tell what's going on here because both Mars and the moon are moving. But as it's not Mars is not moving past the moon. It's actually the moon moving in its orbit past Mars. The moon is the faster moving of the two. And so it's actually the moon that's moving. So if it's clear sky, if it happens to be a clear sky Monday night, go on out, get a pair of binoculars, and at 9:50, take a look at Mars for the next 10 minutes or so, and watch it pass by the moon, which is just a little bit past first quarter. There we go. Just go back out again. Go back down and just zoom out a bit. Now I want to turn around here to face the north because I'm going to do a search here on the comet. And let's take a look. Whoops, I turned off the date and time window. Let me do a search for the comet here. Here it is. That's comet C 2022 E3 ZTF. So let's do this. There it is. And what I will do is just notice where it is. First of all, notice that here's the Big Dipper. I'm looking very much in the northern part of the sky. And so here's the Big Dipper. And here is the North Star. You can see that if I think of this line, here are the pointers. I draw a line from the pointer stars in the bowl of the Big Dipper over to the Polaris. Then the comet is actually above them. And it's going to move a lot. Let me move by a day here. So I'm going to move by a day. And notice how the comet has moved. And it's going to move again the next day. So you can either find out how to put the comet into stellarium. You have to do that by hand. It's not hard. And if you do a search on the comet and ask, how do I put this in the stellarium? The instructions are easy to follow, but they're going to be different for every platform. And so, do your own search, or you can use the little app that I showed you to find the comet for the next several nights. So it's going to be brightest on Tuesday. That is when it's closest to Earth. It's going to be brightest in the sky. It'll be barely naked eye, so you have to be, under dark skies to see it. But take out some binoculars and find the comet in the sky. And the nice thing is that it's in the northern sky, and it's up all night. It's never going to set because it's so close to Polaris. But in the next couple of days, or the next week or so, it's going to rise up a bit more, and then it's going to dive down out of the night sky, and we won't be able to see it anymore. So this is the time to see the comet, and it's worth seeing. It really is. And if you zoom in on it, you'll know it's a comet because it has a slight greenish appearance, and you'll even see a tail, a slight tail around it. So pretty cool. So I hope you enjoy learning all about light. Light is the greatest tool that astronomers use to understand the wonderful universe that we live in. And so enjoy learning about that. And we'll continue talking about applications of this next time. So until then, have a great week, and I'll look forward to seeing you then. So until then, bye-bye.